So this is the test number 9. First question. Consider the expressions below about action and reaction forces. They are equal in magnitude. They act on the same object. Their directions are opposite. So what they are asking is what are the true expressions? Okay. So according to Newton's third law, action and reaction force are always equal in size and opposite in directions, and they always act on different objects, not on the same object, right? So if you take like two objects, let's say object A and object B, when they are in contact, so this force is created by B on A. This force is created by A on B. So it is by A on B. So by changing this preposition, you can always identify the reaction force. By B on A, then there must be a force as by A on B. So those are the action and reaction forces. They are always acting on the other object. So all action reaction forces cannot be on the same object. They always act on different objects. So the answer for that should be they are equal in magnitude. So only B is wrong there. They act on the same object. They are not acting on the same object. So only A and C are true. So the answer should be third one for the first question. Okay, second question. When a ball weighing 0.05 kilogram at rest is hit with a bat, its speed increases to 70 meters per second within 5 times 10 to the minus 4 seconds. Force acting on the ball is. So that we have a ball with a mass 0.05 kilogram and it is at rest initially. Then its velocity increases to 70 meters per second due to a force. This is the impulsive force acting on the ball. So in that case, we can use this equation. Force is equal to rate of change of velocity. This is the change. If you divide it by time, then it becomes rate of change of velocity. So the mass of the ball is 0.05, velocity is 70, minus mass of the ball 0.05, initial velocity is 0, divided by time. Time is given as 5 times 10 to the minus 4 seconds. So just do the simplification. 0.05, you can this 5, 0.01, then 0.01, this becomes 0.7 times 10 to the power 4. So this should be 7,000 newtons, meaning it should be 7 times 10 to the power 3 newtons. So the answer there should be the second one for the second question. Third question. Force required to fall an object of mass 5 kg at an acceleration 2 meters per square second downwards is. So we have given these options. So the mass of the object is 5 kg. So what they ask is the force required in order to have that acceleration. So the acceleration they have given is 2 meters per square second downwards. So if I mark, this is the weight, 50 Newton. So this is falling down at a less velocity than 10 meters per square second. So we should know that the force to be applied should be upwards on the object. Then just simply apply Newton's laws. I'll apply Newton's laws downwards. That is F equals ma. 50 minus F equals mass 5. Acceleration is 2. That acceleration is downwards. Then 50 minus this is 10 equals F. So F is equal to 40 Newton. I have marked 40 Newton upwards. I got a positive value, meaning that the direction I marked the force is correct. It is 40 Newton. So it should be upwards. So it is confirmed that the force to be applied should be upwards. So the answer should be the third one for the third question. The fourth question, as shown by the image, a water beaker is placed on a trolley. The knob is attached to the bottom of the beaker by a string. Arrangement of water level and knob as trolley accelerate as shown by the image. Okay, also this is a famous question. We have this trolley that has an acceleration. Let's say it is moving at an acceleration simple A to this side. So by experience, you know that when something accelerates containing a liquid level should arrange like this. So we know that, right? By experience. Liquid level arranged like this. If the acceleration increases, the inclination of the liquid level also increases. The thing is, we have to figure out the form of the knob attached to the string. Okay, I will draw that knob here like this. If you can see that at this side, the water level is at a higher length than this side. So this is H1, this is H2, meaning that at this side it creates a higher force, higher due to higher hydrostatic pressure. At this side pressure is high, P1, than this side. Pressure is low at this side. So this pressure imbalance at these two causes a force on this object to this side. But relative to the vessel, this knob should be at rest. Relative to the vessel, right? So this force due to pressure imbalance should be balanced by a force. So the only way that this pressure force can be balanced is having a component of tension. So we know that tension of this is the tension of the string. So you can get a component of the tension by inclining to this side. So if you think about this tension, it creates like T cos theta to the other side. Then this T cos theta and F would balance out. So the knob would be at rest relative to the vessel. Then this F and this T balances out there. If the string is like this, right? If it is formed vertically, then this tension cannot create a component to this side. It is obvious, right? Because it is normal to the direction of the acceleration. Therefore, the only way is that the string has to bend like this. I mean, it has to incline like this. Then this tension can create a component to the other side like this. Let's say that component 2 cos theta, given that angle is theta. So the string has to form like this. So the correct answer for that should be the third one. So that shows the correct formation of the knob and the water level. Fifth question. Beaker with height 20 centimeters contains water to height 12 centimeters. Given that its diameter is 5 centimeter, maximum acceleration of the trolley without spillage of water is. So this also is a kind of a similar question. The diameter of the beaker is given as 5 centimeters. 5 centimeters. Then height of the beaker is 20 centimeters. Then there's a water level. This water levels, it is at a height of the water level is 12 centimeters. Okay, so this is the water level when it is not moving. But we have to give this an acceleration to a side. So you know that when this accelerates to this side, the water level inclines like this. What they ask is without spillage of water. So the maximum inclination of the water level should be like this. It is so from this side it rises, and the other side it falls by the same amount, right? Since this is 20 centimeter, this length, and this is 12 centimeter, this length should be 8 centimeters. Okay, so this is 8 centimeters. So if it is 8 centimeters, since this fall and the rise should be 8 centimeter, then the fall also should be 8 centimeter. It is a uniform, kind of symmetrical to both sides. Then this height should be 8 centimeter. Meaning that this should be 16 centimeters. And this is 5 centimeters. Let's say the angle of the inclination as theta. So that those lengths should be figured out first. Then they are asking for the acceleration, the maximum acceleration that this can go without spillage. Okay. There's this equation for this tan theta. I'll just prove the equation to show. So you can, to prove that, you have to think about the equilibrium of a water particle on the surface. So the forces acting on that water particle is capital R and mg downwards. Then this angle is theta. Then this angle also becomes theta. So I'll apply F equals ma upwards to the water particle. That is R cos theta minus mg equals 0. So R cos theta is mg. Then I'll apply horizontally. Horizontal component of should be R sin theta. So I'll apply F equals ma. So R sin theta is the only force horizontally on the water particle. Mg is normal to that, right? So R sin theta equals mass of the water particle is taken as a simple m, and the acceleration as simple a. Then I'll just divide first equation, second equation by first one. So R sin theta divided by R cos theta. R cancels off, sin theta divided by cos theta is tan theta equals ma divided by mg. M cancels off. So tan theta is simple A over G. So in the theory, normally you have to remember this equation. So you can use that equation in MCQs, right? Not for essay questions. This can be used for MCQs. Tan theta is equal to A over G. Acceleration over the gravitational acceleration. So this one, I'm going to use that one here. Tan theta is equal to A over G equals, I can write tan theta thinking of the lengths of this. So if we consider this triangle, what is tan theta in lengths? This is the opposite side, this is the adjacent side. Opposite side divided by adjacent side is equal to A over G. That is tan theta. Opposite side is 16, adjacent side is 5. Opposite side 16, adjacent side is 5. 16 divided by 5 is tan theta. So A over G is equal to 16 divided by 5. Not 8 divided by 5, right? Many students have taken 8 as mistakenly. It is not. It should be 16 divided by 5. So what they ask is this simple A acceleration. Okay, simple A divided by G is 10, 16 over 5, 1, 2, 1, can cancel, then A equals to 32 meters per square second. By just simply solving that, you can take acceleration as 32 meters per square second. So the answer for the fifth question should be fifth one. Sixth question, it is from work. The graph below shows the variation of force capital F with displacement S. Work done by force F is. So they have given a graph to show the variation of the force that changes with the displacement. So this is the force, Newton, the displacement S in meters. So the graph is like this. This value minus 2, this is 6. Then this value they have given as 2. And this value 4 here. So all you have to do is to find the work, you just have to find the area of this graph. So some students mistakenly think that since this displacement is negative, that you would have to like subtract this area from this one. No, you don't have to subtract that. You just have to get the total area. If I further explain that, just think about this, right? This zero displacement means origin. Origin, right? Zero displacement means origin. Displacement to this side positive, then this side is negative. Still, the force acting on the object is positive. All the forces are like positive, right? All the forces are above x-axis. So the force is always positive, meaning if an object is here, direction of the force is always this side. And also, the object always moves towards the same side. So the displacement and the force both are to the same side, same direction. So there cannot be a negative work done on the object. So the work from here to here and here to here, both should be positive, meaning that you have to add all the areas here. So let's find the area. So this is the trapezium. So how do you find the area of the trapezium? Sum of length of parallel sides. So this side, that is 2. This side, lengthier side, that is 2 here, then there are 6 here. So length of this side should be 8. So sum is 2 plus 8 divided by 2 multiplied by the height between the parallel lines. So the height between the parallel lines is 4. 1, 2, 10 times 2 plus 8, 10, 10 times 2, 20. So this should be 20 Newton seconds, sorry, Newton meters, so 20 joules. So if you get a graph like this, you just have to add all the areas. But if you get a graph that goes below, let's say if I further expand this, if this graph goes below x-axis like this, meaning now the force acting to the opposite side. So this area gives us a negative work in that case, right? So you have to be careful there. Only force is negative, then work done would be negative there. Here, you just have to add both. You have to check whether the displacement and force are on the same side. In that case, if they are on the same side, you just have to add all the areas in order to get the net work done. Yeah, so answer should be 12 joules for the sixth question. That is the third answer for sixth question. Seventh question. A mass m falls from a height h under gravity. Given that 0 point of potential is ground, speed of the object when half of potential energy of mass is lost. Okay, there's this mass, symbol m. It is at a height, symbol h. So this line is 0. That is p equals 0, right? That is the ground level. So what they ask is when half of this, so this has a potential energy at this level. This has a potential energy that is mgh plus mgh. So what they ask is speed when half of that potential is lost. So it is obvious that when object moves h over 2 distance from the top, half of the potential energy is lost. So that is so this should be the amount of potential energy lost when it reaches from here to here, mgh over 2. So that lost potential energy has to convert into something. So that is a mechanical conservation law, energy conservation law. That half of that potential energy has to convert into kinetic energy. There's no any other type of energy here. So mgh should be equal to half mv squared. mgh over 2 should be equal to half mv squared. So half cancels off, m cancels off. Then gh equals v squared. V is equal to gh root. So that is the velocity when it loses half of the potential energy of it. So the answer should be the second one for the 7th question. 8. A pendulum to measure the speed of a bullet is shown in the image. Bullet with mass m penetrates and is stuck in the pendulum with mass capital M. Then it rises to a height h. The speed of the bullet is. So the speed of the bullet is simple v. They are asking for an expression for that. Okay, so this is the pendulum that has a mass capital M. Then the bullet with mass simple m moving at simple v collides with this pendulum. So what could happen? So initially the capital M is at 0, right? I mean the velocity of capital M is 0. Then due to the collision, this gains a velocity. Then it moves upward somewhere here. Let's say it moved somewhere here. Now the bullet is stuck in the block. So we can consider that to be one object. So the mass of that should be capital M plus simple M. And it is stops here. So the maximum height is h. They have given it as simple h. So you need to get an expression regarding v, h, those stuff, right? Okay. So there is a collision. At this point, there is a collision. So we know whenever there is a collision, there is a energy loss, mechanical energy loss in most cases. So for the collision, we cannot apply that energy is conserved. We cannot say that energy is conserved. So, but we can apply momentum conservation. Momentum is conserved no matter what, right? For a system considered. Okay, for the collision, I'll apply momentum conservation. So before collision, momentum before collision is only this is moving, only this part has momentum. So that should be mv, this is the momentum before collision. Then after the bullet is stuck in capital M, then both acts as one object. Let's say that system gets a velocity like simple w. Then I can say M and capital M both acts as one object and gains a velocity w. So this is the momentum after collision. We need an expression for this w, which we will use later. So w is equal to mv divided by simple M plus capital M. So this is velocity of the system at this instant when the bullet hits the block. We'll keep that for now. Okay, then after that, what happens is this whole thing goes up, moves upwards in a circular motion, and it stops somewhere here. So after that, there's no collision. Then after that, if you know, for circular motions, we can apply the energy conservation law. So energy at here is equal to energy at here because energy is conserved. Okay, so energy here is, I'll take P equals 0 line to this. So the energy here is half. Now we have to consider both, right? There's bullet stuck in here, right? So the mass is capital M plus simple M. Velocity, not V, not simple V, velocity should be W. So that is the velocity of capital M plus simple M. So W square is equal to, when it reaches here, it stops here, so there's no kinetic energy here. It only has a potential energy. And the potential energy of should be capital M plus simple M GH. Then I can cancel capital M simple M that term. So we get half W square equals GH. W is not what we want. We need simple V. Here we have this term for simple V. So this can be substituted here. So this W, instead of this W, I can substitute this thing. So half W square should be mv divided by simple M plus capital M square equals GH. Okay, now we have this one, and it only includes simple V. That is what we need. Then I'm going to subject simple V. So 2GH, I move this whole calculation here. Cross multiply, 2GH goes to the other side. Then capital M plus simple M divided by M squared. This is equal to V squared. So I just cross multiplied all the things to the other side. I need to subject V. Right? Then V squared is equal to 2GH squared. Then just take the root of both sides, 2GH root, capital M plus simple M divided by simple M. So this is the velocity. So this is the velocity of the bullet. So here we have applied momentum conservation for the collision and energy conservation for the system that moves upwards in a circular motion. So the answer for that should be capital first term, right? So the answer for that should be root 2GH. Yeah, should be first term. Ninth question. A simple pendulum with length L is held so it makes an angle theta with vertical. When it is released, the speed it gains at the bottom of its motion is. So we have a simple pendulum and it is held like this in this position. The angle that it makes with vertical is theta. It is held like this. So what they ask is, so you release that here, then it reaches here. So what they ask is the velocity that it gains as it reaches this position. Right? As it reaches this position. Okay. So you know that this is a circular motion in a vertical plane. So for that, the mechanical energy is conserved. Right? Okay, so length of the string is simple L. So you can see that when this object moves from here to here, let's say this is P equals 0 line. When the object moves from here to here, this loses potential energy. Since it is lowering, it loses potential energy. Then potential energy here is 0. because this is P equals 0 line. That potential energy has to convert into something that completes convert into kinetic energy of the pendulum. Okay, so that is energy conservation. So potential energy here converts into the kinetic. So potential energy here, let's say this height as simple h. So potential energy here is mgh, that is equal to half mv square. Kinetic energy here. Here there is no potential energy. So whole potential energy converts into kinetic energy. Then mn cancels off, then gh equals half v squared. Then v squared is equal to 2gh. But they are not asking this v in terms of simple h. What they ask is in terms of simple L. So if we consider this triangle, this is the hypotenuse, then this becomes L cos theta. This becomes L cos theta. So what you need is simple h. Right? From here to here, this is the same string. Length is simple L. This total length is simple L. This length is L cos theta. Then this simple h should be L minus L cos theta. Length of this part should be L minus L cos theta. This is the length of the string L minus this length is L cos theta. This is the adjacent side, so it should be L cos theta. L minus L cos theta is simple h. Then you can take simple L out. Inside the brackets, it would be 1 minus cos theta. This is equal to v squared. The v is equal to 2gl 1 minus cos theta root. So this should be the velocity of the object at here. So the answer for that should be fourth one for the ninth question. 10th question. If the friction coefficient related to the image is 0.5, maximum of W is, so 60 Newton is in equilibrium. So we have given an image. There's this object that has a mass, weight, 60 Newton. 60 Newton. Then there's a W, and this is 90 degrees. This is 45 degrees. So what they ask is the maximum weight that this can hold. Okay. So this is a friction question. There's a friction acting here. Let's say that friction is capital F. Since they are asking for the maximum weight, here also the friction acting on the object also should be a limiting friction. In that case, we can apply F equals mu r. You know that when you apply equations here, capital R should be 60 Newton, right? You don't have a right equation for that since it's MCQ. So it is obvious that normal reaction acting here should be 60 Newton because there's no any other vertical forces acting on this object. So capital R should be 60 Newton. Then let's find the friction. So F equals mu r. Friction coefficient is given as 0.5 times R is 60. So this half times 60, that should be 30 Newton. So the friction acting on here should be 30 Newton. Okay, now we have these values. For this one, what about the tension acting here? Tension should be W, right? Because this is in equilibrium. Tension at this part of the string should be W. And here also the tension should be W. It is action reaction forces. if the weight of the object is W, then tensions also of this part of the string should be W. Okay. Then if this force is 30 Newton to the other side, tension of this string, whole system is in equilibrium, right? So to other side as well, 30 Newton of tension should be acted like this. Then, but we don't know the tension of this part of the string. So we'll get that tension as capital T. Right. Then I'm going to think about the equilibrium of this point here. Horizontal equilibrium. T cos this angle 45. T cos 45 minus 30. 30 is other side, minus 30 equal to 0. This is equilibrium. So T cos 45 is equal to 30. Then I'm going to apply to A vertically upwards. That is also T cos 45, right? Minus mg. In this case, it is W. Tension here is W is equal to 0. Then T cos 45 is equal to W. So this is first equation, then second equation. You can notice that both sides has T cos 45. Then what should be W? W should be 30 Newton, right? Because these two sides same, then these two sides also should be same. The W is 30 Newton. So that is the maximum weight that can be attached here. So this won't slide to this side. So this whole system is in a limiting equilibrium situation, right? That's why we applied F equals mu r for this question. So answer should be fourth one for the 10th question. 11th question. Part of a chain with capital N is on a table. If static friction coefficient is mu, maximum length of the part hanging by the table is. Okay, so there's this table. Then there's a string, chain on the table. I'll draw the chain a bit thicker so you understand that. So the total length of the chain is capital L. They have given it as capital L. Only a part of the chain is on the table, then the remaining part is hanging by the end of the table. So what they ask is maximum length of the part hanging by the table. So I'll take that maximum length as simple x. That maximum length as simple x. So if the total length is capital L, length on the table should be L minus x. Total length is capital L. If this is x, then the part on the table should be L minus x. Okay. Then you just have to do a simple force equilibrium case here. We know that at this part there's a friction acting to the other side. Let's say that friction is capital F on this part. That is capital F. Then the weight of this part, I can say that weight as L minus x times g. That is mg. I use only lengths here because this is MCQ. I'm not going to apply cross sections, lengths, and density of these. Right? So you don't have to. Because they are uniform for the whole chain, you only have to apply a length there. Length is the only variable here. So I can write mass in terms of length here. Even if you write those stuff like density and cross sections, those gets cancelled off, right? So here I will, instead of mass, I'll use length here. So this length L minus x g. That is only for this part, and for the other part, length Mass is x. I'm using only length for the mass, xg. So this is the weight of this part. Then, in order to find friction, we need to get normal reaction force acting on this part. I will say normal reaction as capital R. Then it is obvious that normal reaction also should be equal to the weight here, because there is no any vertical forces. So that should be L minus xg. Okay. So all the forces required are marked now. Then I'm going to think about equilibrium of this part. Let's say to this part, the friction is capital F. Then there's a force acting on, I'm thinking only about the equilibrium of this part. Friction to the other side is capital F. Then the force due to the weight of this part, there's a force acting on this part to this side. So that force should be equal to Sg. So that is the weight of this part. Is held by this part, other part. Then the force acting on this here should be Xg to the other side. So this part of the string is in equilibrium under these forces. So friction and Xg should be equal. Friction and Xg forces should be equal. Okay, friction, we can use instead of friction, I can write mu r. Then mu r equals Xg. Mu r is, I found a value there, L minus Xg. R is L minus Xg. Substitute it here, Xg. Gg cancels off. Then I can get mu L minus X equals X. So what we need is simple X. Mu L minus mu X equals X. X plus mu X equals mu L. Take X out, 1 plus mu equals mu L. Then get 1 plus mu to the other side. So mu L divided by 1 plus X equals X. So this is the length of the part hanging by the end of the table. Length of the string, sorry, length of the chain that is hanging by the, so this is the maximum that can hang there, right? So this also is a limiting friction case. We can identify that because they are asking for a maximum value, right? Maximum of X. So that is answer there should be for the 11th question should be third one, that is mu capital L divided by mu plus 1. Then 12th question. As shown by the image, X and Y wooden blocks are submitted to a horizontal force of 12 Newton. If the kinetic friction coefficients are 0.05, tension of the string is. So they have given a kinetic friction coefficient, meaning that this it hints that this system should move, right? It is not at rest. It is not in equilibrium because they have given kinetic friction coefficient. So one of the mass is 2 kilogram. Then other mass is 4 kilogram. Then there's 12 Newton of force is applied. I can mark weights 20 Newton, 40 Newtons. So the normal reactions also should be 20 Newton and 40 Newton. So I just apply R values like this because there's no any other vertical forces acting on the objects, right? If there are vertical forces, you cannot say that R and Ng is always same. It is not always same, right? You have to be careful there. But here there's no vertical forces acting on the system. I mean, except R and Ng. So R and Ng should be same in those cases. Okay. I'll just apply kinetic friction coefficients and calculate the friction values acting here. Let's say this friction is F1, then this friction is F2. So F1 is equal mu R1. Mu is 0.05 friction coefficient times R 1 is 20. So this should be 0.5 times 2. That is 1 Newton. So 1 Newton is the friction acting here. Then I'll calculate F2. Coefficient 0.05 times 40. Multiply by 10, 0.5, then multiply by 4. 2 Newton. So here the friction is 2 Newton. So 1 Newton and 2 Newton. Then, so what they ask is tension of the string. This tension. So in order to find that, it is obvious that this system has to accelerate, right? There's a 12 Newton force applied to this side, and to the opposite side there's only a 2 Newton and a 1 Newton. That is 3 Newton to the opposite side. In that case, there's a unbalanced force to this side, so this system has to accelerate. First, before finding capital T, you have to find the acceleration. Let's say acceleration of the system as simple A. Then to the whole system, I'll apply F equals ma to this side. So to this side, for the system 12 Newton, this T and T cancels off because they are internal forces here. But 1 Newton and 2 Newton, they are the opposite side. But they are minus 1 and minus 2 equals mass of the system 2 plus 4, that is 6 times acceleration. So this is 12 minus 3, 9, 9 equals 6a. A equals 9 divided by 6, 3 divided by 2, meaning acceleration is 1.5 meters per square second. So that's the acceleration of the system. Once you get the acceleration, then you can apply equations for this part only in order to find tension. To 2 kilogram, F equals ma to this side. So what are the forces acting on that horizontally? T, tension, to the other side minus 1. That's a friction, equals mass 2, acceleration, that is acceleration 1.5 or 3 over 2. T minus 1 equals 3, then T equals 4 Newton. This is the tension. You could apply F equals ma to 4 kilogram as well to get the tension, but it is a bit difficult, right? So just apply F equals ma to 2 kilogram only. There are like less forces involved here. In that case, you can find the tension. So the tension should be 4 Newton. The answer, 12th question, should be 2. 13th question. A block A is in contact with vertical side of a trolley as shown by the image. If the static friction coefficient is 0.25, minimum acceleration of trolley to keep the block A without falling is. So we have a trolley. Then there's this capital A object kind of like placed, it is in contact with the trolley, on the face of the trolley, front face of the top trolley. So what they ask is the acceleration. So this capital A won't slide downwards. So you know you have to have acceleration to this side. So A would stick. It look kind of like stick to this face. Okay. So then I'll apply forces acting here. If the mass of that capital A is simple M, weight should be mg downwards. Then along this surface, there's a friction acting. Then this friction should be able to balance out this mg. So this won't slide downwards. Then there's another force. Due to contact here, there's a normal reaction force acting to this side. So those are the only forces acting here. So then apply F equals ma vertically and horizontally. Let's apply horizontally. F equals ma. So the horizontal force acting here is capital R equals mass of the trolley times symbol A. If I apply vertically upwards, F minus mg, so it is not sliding, right? So that is a requirement. So acceleration vertically should be 0. Then here F equals mg. So we know that this F is mu r, right? It's also a limiting case. They are asking for the minimum acceleration. So whenever they say like minimum and maximum, always a limiting case. So you can apply mu r. Just apply mu r. Instead of F, I apply mu r. Mu r is equal to mg. So instead of r here, I have this. R is equal to ma. That's equal to mg. Mm cancels off. Mu a equals g. So a is equal to g over mu. G is 10. Mu is 0.25. So you know 0.25 is 1 over 4, right? So if 1 over 4 goes to the numerator, it becomes 4. 4 times 10 is 40 meters per square second. So that's the acceleration required for the trolley, so this won't slide downwards. So if we go at a higher acceleration than this, in that case also this won't slide downwards. That's why they ask minimum acceleration. So that's the minimum requirement for this to happen. So the answer for the 13th question should be 5th one. Moving on to the 14th question. Two pendulums with same length are arranged initially as shown by the image. When the inclined pendulum is released, it hits another pendulum and moves as a one pendulum. Maximum height compound pendulum moves is. Okay. There's this pendulum M1, and there's another pendulum here M2. Then this pendulum is at a height simple d. It is at a height simple d. Then M1 is released. So what happens? M1 moves here in a circular motion and it collides with M2. Let's say just before collision, the velocity of M1 is u. That is the velocity of M1 just before collision. So after the collision, what happens? They attach together. Hello? Daniel? Dahil? Oh. Oh, Dahil. Then this collides here. Let's say the velocity of that compound object is simple v. Since it is a compound mass, I can take that mass as m1 plus m2. So this is the velocity of m1 just before collision. Simple v is the velocity after collision when they attach. That's a common velocity. But it is still here. So then what happens? M1 plus M2 moves upwards. Like this. In a circular motion, let's say that length, height is simple h. So this is what happens here. So what they ask is actually this simple h. That's the maximum height this reaches. Okay. Here, First, this simple h you have to calculate in terms of m1, m2 and simple d, right? So I have to get rid of these terms. Okay. First, you have to get a term expression for simple u. For that, you can apply energy conservation from here to here. So energy here is equal to energy here. So when m1 reaches from here to here, it decreases its potential energy. So m1 decreases its potential energy. That decreased amount should be m1g_d. That is how much it lowers, right? m1g_d. So that potential energy has to convert into kinetic energy. Still, I am applying the equation only to m1, right? Only to m1. So that is converted into kinetic energy of m1. So I have mentioned that velocity in m1 gas is u. Then half mu squared, m1 cancels, so 2gd equals u squared, 2gd root equals u. 2gd root equals u. So now we got expression for simple u. Okay, then we have to think about the collision between m1 and m2. So to collision, I have to apply momentum conservation. Collision between m1 and m2. So before collision, momentum before collision is m1u. I'll just put u there, m1u. After collision, they attach together, so mass is m1 plus m2. Just after collision, it gains a velocity v. So velocity here is v. Okay, so m1u divided by m1 plus m2. So this is v. Okay, then again, so now the collision is over. m1 plus m2 starts to move upwards. So for that motion, I can apply energy conservation. So what happens is, here it has a kinetic energy only. That is half m1 m2. Velocity is v squared equals to that kinetic energy here converts into potential energy. Completes converted to potential energy because object stops here. There's no kinetic energy here. It only has a potential energy. So the potential energy gain is m1 plus m2 g. Height is simple h. The simple h is what we need to find. m1 m2 cancels off. Half v squared. So we have a term for v. I'm going to substitute it here. So v is this one, right? m1u divided by m1 plus m2 squared equals gh. Half m1 divided by m1 plus m2 is squared. U is squared. So we earlier find u. So u squared is equal to, if you square both sides, it is equal to 2gd. This is gh. Then g cancels off, 2 cancels off. m1 divided by m1 plus m2 squared times d is equal to h. So then this is a simple calculation. You just have to substitute these values in order to get that. So d is written in terms of masses and this height, this side. So the answer for that should be second one, right? Second one should be the answer. So what we did is we applied conservation law to find simple u. Then applied momentum conservation to find this v. Then again we need to find simple h. Again we applied conservation, energy conservation to find simple h. So that is what we did in order to find this height. So we applied energy conservation 2 times and momentum conservation once. 15th question. from a height 20 meter, a mass 0.5 kilogram is dropped. Kinetic energy of mass when it hits the ground is. So there is a height 20 meters, 0.5 kilogram is dropped, initial velocity 0. So what they ask is kinetic energy it gains as it hits the ground. As it hits the ground. Okay, so we know that when it hits the ground, so now this object has potential energy. That total potential energy has to convert completely into kinetic energy here. So meaning potential energy here is equal to kinetic energy as it hits the ground. So you just have to find the potential energy, which will be equal to the kinetic energy. So I can say, so the potential energy equal. So potential energy is mgh. Mass is 0.5, g is 10, h is 20. So 20 times 0.5 means half. 10 times 10, that is 100. So kinetic energy is 100 joules. So that's like the easiest question here. So the kinetic energy gains as it reaches the ground is 100 joule. So the answer for that should be third one.